So, hello everybody, I'm Marta De Simone. I'm a fellow at the European Southern Observatory in Garching in Germany. And I would like to thank the organizer for the opportunity to talk to you today about my work on the chemical nature of young protostars. So to give a little bit of context, we are talking about solar type star formation process that is here schematized in the principal phases of this process. We have that aprestellar core that collapse, form a protostellar core where part of the material is accreted onto the central object and the other part is ejected through jet and outflow, then a protoplanetary disk where planets were thought to form, and then eventually a planetary system. To understand the latest stage of this formation, it is important to well characterize the early stages that are characterized by the protostellar phase, this initial phase right after the collapse. But recently, there were evidence that showed that the planet formation could actually start early in the disk, so not in the protoplanetary disk, but already in the protostellar phase. Thanks to some works based on the mass solids in disks compared to the mass solids present in the exoplanets, or the presence of ring and structure already in the class 1 stages that are evolved protostars. So understanding the chemical complexity and content of the protostellar phase, it is important to understand what a future forming planet can inherit. But the chemical content of the protostars is actually very far to be understood completely. It has been always studied at millimeter wavelengths. This is because some peculiar objects were discovered towards protostars, and are these hot corinos. In particular, the fact that the central object is very hot due to the accreting material that eats the surroundings. We have that the dust grains that are coated by ice mantles and enriched of hydrogenated species formed in the previous prestellar phase are sublimated. So all the species in the grain are sublimated into the gas, and a complex chemistry is triggered. So these objects that are compact, hot, and dense, they are enriched in the so-called interstellar complex organic molecules, that are the species with more than 6 atoms and containing heteroatoms, so nitrogen, oxygen. But naively, we could think that every protostars possess a hot corino region, and this complex chemistry, it is important to be characterized because can be inherited by forming planets. However, when we study this object at millimeter wavelengths, because at these wavelengths, these icons have a bright emission, we see that not every protostars has a hot corino region, but actually the hot corinos are very few. We have 25 icon-rich hot corinos, and if we focus on methanol, that is the simplest and brightest icons, we have maximum 40, thanks to the large survey done so far with ALMA, for example. But not only, if we observe several protostars and several hot corinos, we see a difference in their millimetric spectra. Here is an example from the ALMA Faust large program, and we have, for example, one hot corino that shows a forest of lines, but other hot corinos that show emission of lines but less complex, or we have protostars that do not show at all emission of these species. Why we have this difference? Why there are very few hot corinos? There can be several possibilities. Mainly, the first that we can think of are observational biases or presence of Mosquet structure that can hamper the detection of these species, or are chemical intrinsic diversity due to a different grain mantle composition. The first case, the observational biases, can be due because these objects are very young and embedded in their natal environments that can be so optically thick to obscure the emission of the molecules. And this is what we try to investigate, observing this system, IRAS-4A, in the Perseus cloud. Here, there is the continuum and millimeter emission, where we see that IRAS-4A1 is the brightest in millimeter continuum emission, while IRAS-4A2 is the weakest. If we go to observe in molecular emission, this is one of the icons, we see that the emission is only towards IRAS-4A2, that is the weaker in millimeter continuum. while IRAS 481 do not show any emission from any icons. So what we did was to move from millimeter wavelength to centimeter wavelength, because at centimeter, the dust is more likely optically thin. And this is what we found observing methanol, the simplest and brightest icons. But actually, with the VLA, we observed that with the VLA. And we observed that methanol was popping up towards both protostars, showing that the IRAS 481 source was hosting also hot Corino, but it was just hidden by the dust. But this can explain why some hot Corino can actually be hidden, but it doesn't explain the difference among the spectrum of different hot Corinos. And to investigate that, we tried to retrieve the mantle history, because a different spectra could reflect a different grain mantle composition. So the grain mantles are formed into the prestellar phase, where the grain are coated by these ice mantles, and the species start to be hydrogenated. So we form species like CH4, H2O, and methanol and ammonia. But studying these mantles directly is very challenging, as they are very embedded. So a possibility is to study them indirectly once these species are released into the gas in the protostellar phase. And among these that are the major as mantle component that I showed here, methanol and ammonia are the best critical tracers. This is because they can be studied in the centimeter wavelength simultaneously, and they can be observed at high angular resolution to observe only the central core, where the dust is more likely optically thin, as I showed you before. And additionally, more importantly, we know very well their formation path, so that we can relate the ammonia over methanol abundance ratio with the condition of the cloud before the collapse. So we measure the abundance of these two species in the protostellar phase to retrieve the condition at the time of the formation, so in the prestellar phase. And this is an example of an astrochemical model that shows you the abundance of ammonia and methanol with respect to time in the prestellar phase. And we see that ammonia forms early because it's due to the hydrogenation of nitrogen that is quite straightforward. But methanol is formed after because it's formed from the hydrogenation of CO. So we have to wait that CO is formed. So if the collapse starts early, we have a grain mantle that is full of ammonia and poorer in methanol. The other way around if the collapse starts after. But this depends also on the temperature of the dust and also on the density. And I will show you later. So what we did was to observe the same system of before, the IRAS-4A system, plus this IRAS-4B source that is 30 arc-second away from the main binary system. And what we see here, we have ammonia observed with the VLA and methanol here on the right. And we see that we detected compact emission of both methanol and ammonia on all the three protostars. We had multi-lines, so we could do a multi-line analysis. And in particular, we did a non-LTE to account for the line opacity and the non-LTE effect. And what we did was to constrain the physical properties of the two species, and they were tracing the same gas, so we could derive the abundance ratio and constrain thanks to the combination of centimeter and millimeter wavelengths, because with centimeter only, we could not give this abundance ratio so constrained. So we constrained the abundance ratio towards the three protostars, and we found that the values were quite similar among the three protostars. So that suggested that they were formed from pre-collapse material with similar physical condition. And this could be a bit obvious maybe for the binary system because they can be coavial and formed from the same cloud. But it was not so obvious for the third source that was far away. So we tried to estimate and give an estimate for this physical condition, comparing the observation with astrochemical model. I will not go into the detail, but for the sake of time, but you can ask me if you're interested. So we here is the same model that I showed you before, but this time I'm showing you the ammonia over methanol theoretical prediction with respect to the dust temperature at different density and in a snapshot of time. And we see that the curves decreases due to the fact that increasing the temperature, the resident time of the nitrogen to form ammonia is on the grain is less than the one of CO. So that's why we will have less ammonia when we increase the temperature. And then we compared these curves with the observation that are shown in this colored band. And what we can see is that what we could give a constraint only on the temperature, but already that was giving us a lot of information. So we see that the temperature should have been of around 17 Kelvin. And we are talking about the really central zone. We are talking about 60 AU. That means that at 6 AU, the prestellar core should have been of 17 Kelvin, but it's a bit too warm for what we are used to. Indeed, at the prestellar core at this temperature, we expect something about 7-10 Kelvin. So if we go to look at the region that is hosting these protostars, we see that the region is actually warm, so it has this temperature in the zone where we are less dense. So what we thought is that maybe these sources went through a premature collapse, and I explain myself a bit better. So in a typical scenario, we are coming from a warm and less dense cloud that then evolved to a cold and dense prestellar core that then collapsed, forming this hot core. So what we are saying is that the ice mantle were formed mostly on this first stage. So it is like that this prestellar cold phase was very, very short or was not even happened. So that means that a premature collapse should have happened and maybe could have been triggered by something that happened to the cloud, for example, an external factor. And one thing that ring as a bell is that there would have been other evidence in this region that it could have been bubbles and expanding bubbles that clashed against this region and shaped the region. So that also could mean that it triggered the formation of these protostars. And this is also a work in progress on the other side to try to investigate more if this scenario is still plausible or not. Oops. So to conclude, what I wanted to convey with this presentation is that we are touching a new ground that is the centimeter observation in the study of hot Corino that unveiled a new road in the chemical characterization of this object and more in general of protostars. Indeed, we showed how we can be completely biased at millimeter wavelengths, so we need to go to lower frequencies to be sure that we do not have this bias. And not only thanks to the combination of ammonia and methanol observation, we constrained the chemical, but not only the chemical, also the dynamical history of the protostars in IRAS4A, so on the NGC 1333 region. So the idea to go next is try to understand how this affects also other systems. So the idea is to go to other sources, maybe in other regions, and with the same of different region to understand also what is the effect of environmental effect on this object. And more importantly is to use a multi-wavelength approach. So we need both centimeter and millimeter wavelengths. Now with the upcoming ALMA Band 1, it will be an ideal way to go. And then for the future, with the centimeter facilities, SKA and GVLA, that will allow not only to go for higher resolution and sensitivity, but also large field of view, so a possibility to try to get with some surveys. And why not also with the infrared to study directly this time the ice mantle composition, maybe more evolved sources that are less embedded. And with that, I thank you, and I'm open for questions.
Thanks, Marta. That was excellent timing too. Are there any questions already? Hands up or questions in the chat? I might ask a really naive question first up. So you were talking about these external factors that can lead to premature collapse. How would you trace those? Can you try to observe some of the remnants of these bubbles, or?
So actually we did a work, okay, that is this one. So this is the NGC 3033 region, and is observed in N2H plus with, this is a velocity map. So what we see is that there are various filaments, and that there is a red shifted emission on the north and a blue shifted emission on the south. So there were some authors that indicated that this differentiation in emission, this gradient, velocity gradient, was caused by this expanding shell, they were calling that. And then when we observed with the NOEMA, some SiO emission and methanol emission, we started to see some filamentary structure, and we attributed that to a train of shocks. So this is why we are saying that probably there is a bubble that is clashing against these filaments. And additionally, this is magenta, is an SiO wide spread emission that is very narrow. So we thought that maybe this is exactly this unresolved train of shock. So what we are doing as a follow-up is to look have a higher angular resolution observation of this map to see if we can constrain more this scenario.
Do you know if there are other sources where you can do this as well?
So in these filaments, there are other three sources, the three protostars, that is this SOS13 up here, and there is another one here, IRAS2. And my idea is go to look these IRAS2 sources because it's in the same filament of IRAS4, and try to do the same approach.
Cool. I've been hogging the time. Has anyone got a question in the meantime? Doesn't look like.